Good morning. Myself Dr. S. Priyadashini, heading Department of Mathematics at JJ College of Arts and Science at NMS. So today our course is Abstract Algebra for 3rd BSc Mathematics students. In Abstract Algebra, I have chosen Unit 1 and the particular topic is permutation group. So today we're going to see about the definition, example and some main hints about this permutation group. First, we're going to define what is permutation group. So, a permutation of a set A is a function from A to A that is both one-to-one and onto. So, a permutation of A, it has to satisfy one-to-one function and onto function. In array notation, now we have to consider a set, capital letter A, which consists of elements 1, 2, 3 and 4. So already we have stated that a permutation is a mapping between A to itself, right? So we have to permute A to itself, that is 1, 2, 3, 4 is mapped again to 1, 2, 3, 4. That's the condition. Now we have defined alpha, that is 1, 2, 3, 4 is mapped with 2, 3, 1, 4. That is 1 is mapping with 2 and 2 to 3 and 3 to 1, 4 to 4. Similarly, beta 1, 2, 3, 4 is mapped to 2, 1 to 2, 2 to 1 and 3 to 4, 4 to 3. That's we have defined here. You can able to see that is alpha of 2 equal to 3. That is the mapping of 2 to 3 and the mapping of 4 to 4. Similarly for beta, mapping for 4 is to 3 and 1 for 2. And also we have calculated beta of alpha of 2. So we have to calculate from the back side, that is alpha of 2. Beta of alpha 2 means we have to calculate alpha of 2 answer, then we have to calculate beta with the particular answer of alpha 2. So what is alpha 2? Alpha 2 is mapped with 3. So we have to find the mapping of beta 3. Beta 3 is mapped to where? 4, right? So now we have to calculate this array function beta to alpha. While starting this permutation, we have to go from back side, I mean left hand side to right hand side, okay? So 1, 2, 3, 4 already we have defined the first row. It may not be changed at any occasion. So it is fixed 1, 2, 3, 4. So now we have to find the mapping of 1 from where? From left hand, RHS side, that is from back to front. So in the back side, that is from alpha. So alpha, you can able to see that 1 is mapped into 2. Okay, first we have to calculate for 1 that I have boxed here, and from back side 1 is mapped to 2. Now move to front side, that is 2. 2 is mapped to 1. So the answer is 1 for 1. Similarly, we have to calculate for next term 2. So 2 is mapped to go back, 2 to mapping is 3, and next we have to move front 3. 3 is moving to 4. So the final answer for mapping 2 is 4. Okay, next 3. Go back. 3 is mapped to where? 1 and move forward. 1 is mapped to 2 and the final mapping for 3 is 2. And the final is 4. So last mapping 4 is identical, that is 4 to 4. We have to go front. 4 is mapped to 3 and the final answer is 3. This is the composition in array notation. So we can able to find for many composition. So already I have stated, now I am refining the definition. That is, the permutation group of a set A is a set of permutation of A that forms a group under the composition function. So now we are going to see the example. So S3 is a symmetric group which consists of 3 elements. Set of all permutation on 1, 2, 3 is called symmetric group on 3 letters and it is denoted by S3. So there are 6 permutation for 3 elements because of the formula n factorial. If it contains number of elements is n. So if it contains 3 elements, the number of permutation is 3 factorial. That is 3 into 2 into 1. That is 3 into 2, 6, 6 into 1, again 6. We get 6 number of permutation. So I have explained here. You can able to see 1, 2, 3, that is 3 number of permutation. N factorial is formula 3 into 2 into 1 equal to 6. That is S3. Now we are going to see the what are that 6 permutation in this 3 elements. Okay, 1, 2, 3. That element represents the identity. That is 1, 2, 3 mapping with the same element 1 to 1, 2 to 2, 3 to 3 is called the identity permutation. Next one alpha. That is 1, 2, 3 is mapped with 2, 3, 1 and alpha square. that is alpha is again mapped with alpha. 1 2 3 we get 3 1 2, and beta 1 2 3 is mapped with 1 3 2, and alpha into beta 1 2 3 into 2 1 3, and the final is alpha square beta 1 2 3 3 2 1. If you again and again you will follow the composition method, you will get the repeatedly you will get the again the 6 results. I hope you can understand. That is, if you make the operation composition with the alpha and alpha square, or alpha square and alpha square beta, or whether it may be alpha beta or alpha, you get the resultant, it may be in this 6 category. No other results other than this 6. So this is the final 6. You can't get any more results other than 6. So for 3 elements for permutation, you get only 6 permutation. So now we have to find whether this symmetric group 3 is a symmetric group permutation is a group or not. Okay. So for group, we have to identify whether it is has identity, close, inverse, and associative. Okay. So the shortcut method, we know we have to identify whether it has identity, inverse, and associative. Okay. Now we have to find this symmetric group has this 3 condition. Okay. We know that composition function is always associative. So we have already get satisfied with the last condition. Okay. Okay. Next we have to find with the identity. What is identity? The first permutation I have stated before, 1 2 3 mapped into 1 2 3. That is the identity. Okay. The final is, since permutation are 1 to 1 and on to. So this is the definition for permutation. So if there exists 1 to 1 mapping and on to, finally there exists an inverse function. So S3 is a group. Computations in symmetric group 3. So already we have found alpha square. Now we are trying for alpha cube, whether they exist in the 6 elements or not. Okay, let us find this. You see, from back you have to find 1 is mapping with the 3 and 3 is mapping into 1. So 1 to 1. So for 2, look at the back side, 2 to 1, and 1 is mapped to 2, again identity, and 3 to 2, 2 to 3, identity. So the final result is identity exist. Okay. Again we are checking for beta square. 1 2 3 1 3 2, 1 2 3 1 3 2. Okay, go from back, 1 to 1 1 to 1. Okay, we get 1 to 1, and 2 to 3 3 to 2 2 to 2. Okay, 3 to 2 2 to 3. So this is also an identity function. Next we are checking for similarly beta alpha. While checking beta alpha, you get alpha square beta, which is already stated here, stated there. 6 permutation we have defined for this S3. So when you find again and again new permutation in this S3, you will get repeatedly the 6 permutation results only, rather than not anyone. So simplified computation is S3. So you can verify this. I have just displayed the results. You can able to simply verify. You can check it with the results. Already we know what is alpha, what is beta, what is alpha square, what is beta. Just go and check it. Now we are going to for Sn. Now we have verified this results for S3. Now we are moving for Sn. So Sn is a group which consists of n elements, 1, 2, 3, etc. And the group of n letters is denoted by Sn, and group of all permutation of A is under the composition function. So Sn is a group for the same reason. What is S3? The same procedure we have to follow. And number of elements in Sn is also n factorial. That 3 factorial, here n factorial. So here symmetric group for a square D4. So just we have to rotate this 1, 2, 3, 4, and we have to identify the number of permutation. We can able to see 1, 2, 3, 4, R naught is identity, and R 90 degree. We just have to rotate and start from 2. So 2, 3, 4, 1. Next we have to start from 3, 3, 4, 1, 2. Okay. Next 270 degree, starting from 4, 4, 1, 2, 3. Similarly, we have to rotate it horizontal version. Okay, 2, 1, 4, 3. Next vertical section, that is 4, 3, 2, 1. Next diagonal section, 1, 4, 3, 2. Next again diagonal, 3 to 1 4. That's all. So 4 factorial possibilities. So here is the sum of the results. Every group turns out to be a permutation on some side. So cyclic notation. So you can able to see that is alpha 1 is mapping with the 2, 2 to 3, 3 to 1. So just we can denote it by 1 to 3. That is 1 to 3 denotes 1 is mapped to 2, 2 to 3 and 3 is mapped to 1. In shortly we can write this as a cycle notation. This is a cycle. 4 is the identity, we can just leave it. Similarly beta you can see 1 is mapped to 2 into 2, 1. So 1 to 2 is a cycle notation. 1 to 2, 2 to 1. That's all. Next cycle is 3 to 4, 4 to 3. So you just write 3 to 4. That is 3 moving to 4 and 4 moving to 3. That's all. It's a cyclic notation. So disjoint cycle. Two permutations are said to be disjoint if the sets of elements moved by the permutation are disjoint. So that the permutation moved from the sets are disjoint. And also every permutation can be represented as a product of disjoint cycles. So this permutation is denoted by pi symbol and A be the identity permutation, and while there exists an n and pi of n not equal to a of n, start a new cycle with let b equal to n while we can check this alpha beta case, beta alpha case. It just not satisfies this law. That is alpha beta you get this result 1 3 4 while beta alpha 2 4 3. Thank you.